introduce to you our speaker. It's rather, actually, for me, it's very nostalgic because Professor Wright and I, we sort of professionally grew up at the same time period. He's a little bit younger than me.
I don't look it.
That's in the 70s, mid-70s, late 70s, and early 80s. Those times, again, there's energy crisis. You guys probably don't know the energy crisis. And it was at the beginning of the golden era in combustion. Combustion, there's several periods of golden era. That's one of them. It started from mid-70s, and the mathematicians started doing asymptotics of frame structures. That's the time, okay, they started doing that. And then the laser folks from the physics communities, and then computation was. And it's during that time, Professor Wright came to Princeton, and I came to Princeton too. After I graduated, I first went to GM to work. I wanted to solve the world's problem, but then I think I'll do that. So I came back to Princeton. That's a career thinking. It's okay. I took a big cut in salary. I came here as a postdoc, but that's the best move but anyway, that's that time. Princeton, it was really a very even now, very, very exciting place. And I have a colleague, Professor Fred Bracco. Fred Bracco at that time. And Professor Wright was in his group. And that was the time they proposed and started doing computational simulation of what happens in engines. And also use lasers to see what happens there. That's the beginning. Not every major engine lab or whatever has those things. A computational simulation of what happens in engines and the laser analysis. Okay? And that's the time we started. So Professor Wright since then has since Princeton time, he's also a mathematician at heart, worked at Courant Institute afterwards, University of Courant Institute, the mecca of applied mathematics. There. And then we went to Wisconsin medicine.
GM first.
GM first, that's right, GM first, sorry.
Also tried to solve the world's problems.
Solve the world's problem, yeah. So I can tell you more about GM. Then went to Wisconsin medicine, basically heading up there, continuing the great tradition of medicine. They always have a strong tradition in research. Then he eventually took over that, and there has been an engine research center there for how long?
Since 1946. You can see it on our logo.
Yeah. Okay. Yeah. But then the new logo is probably in the late 80s. They designed it. Gary Bowman designed it. So anyway, so he is what I thought of having a course on engine, reciprocating conduction engines, obviously, is right, is there. And he's lately also agreed to join our EFRC center as a PI. So our EFRC center now covers the whole spectrum, from initial calculations of chemical kinetics all the way to engine simulation. So without further ado, I give it to you, Professor Wright.
Thank you very much, Ed. Thanks for inviting me to Princeton again. I haven't actually been here for about 30 years, although I've visited some of the activities close by to the downtown Princeton. I haven't been downtown for 30 years. Nothing has changed.
DJ Pancake. Try. I think they're more interesting.
So, good morning, everybody. As Ed said, I'm from the Engine Research Center at the University of Wisconsin-Madison. I have put together 9 lectures. They're each about an hour. I'm not sure that I'll be able to get through all of the material in all of the lectures, but I'll try. It would be helpful to know how many of you have had some kind of internal combustion engine course. I know Elliot has. Okay, that's great. So I can assume some things that will allow me to go a little faster. But if there's any uncertainty or whatever, just let me know and I'll slow down a bit. So this just summarizes what I'm trying to accomplish here. We've got 3 days. Today will be devoted to engine fundamentals. We'll look at a review of internal combustion engines, talk a little bit about some of the system issues associated with engines, turbochargers and so on, and then get into some of the combustion process. Tomorrow we'll talk about spray combustion, droplet phenomena, heat transfer and emissions. And then on the last day we'll talk about some applications, diesel combustion, spark ignition engines, and something that's very interesting today, which is low temperature combustion. And then I'll end up with some applications and talk somewhat about the longer term future. So why are we interested in internal combustion engines? As you all know, society relies on internal combustion engines very heavily for transportation, commerce, and power generation. In fact, if you look at this list here, you'll see that they are really pervasive. And that's another reason, by the way, why the Engine Research Center has been around so long, more than 60 or 70 years, is because engines are so important to our society. They power, for example, the 600 million passenger cars that we have on the roads in the world today. And if you just look in the United States, we have 250 million vehicles. That's roughly one per person. 50 million cars were made in the world in 2009. And you can see that's up significantly from 2000. And things are changing. China became the world's largest car market in 2011. A third of the cars produced are produced in the European Union. And 50% of those are powered by diesels. So when we talk about engines, we have to worry about both gasoline and diesel engines. Of course, along with this huge number of vehicles and engines comes fuel consumption. 70% of the roughly 86 million barrels of crude oil that we consume every day are used in IC engines for some sort of transportation. And in the US, 10 million barrels are used per day in cars and light-duty trucks, 4 million in heavy-duty vehicles. So it works out to about 2.5 gallons for every person in the United States every day. And of course, we don't have a lot of it here in the US, so 62% of this is imported. And if you pick a price, here I just picked $80 a barrel, that's about $1 billion a day that we spend on imported oil. This chart, you can spend hours, and I suggest you look at it later. Looking at it, it's a very interesting chart out of Lawrence Livermore, I believe. But anyway, it talks about how energy is used in the United States. You'll see that we use 100 exajoules of energy in the year. And it's partitioned in this way here. 40 out of the 100 is in the form of petroleum. And of course, 70% of that is used for transportation, as we just said, light duty, freight, and so on. If you look at the other forms of energy, natural gas is about a quarter, coal is about a quarter, and then all of these combined, solar, nuclear, wind, so on, are about 14. This is a nice number because it's nice and round here, so you can kind of convert these into percentages very easily. The United States uses 1/5 of the world's energy, so it also puts that into perspective. So we're talking about transportation representing about 28 or 30% of the United States' energy consumption. The other interesting thing about this plot is comparing the gray and the brown regions here. The brown regions are useful work. The gray regions are energy that is thrown away. And you can see that roughly 60% or 55% of the 100 exajoules here is just thrown away because of losses that occur. You know, so if somebody tells you, oh, they're going to plug in their hybrid vehicle and it's going to be a really efficient car, you've got to go back to this diagram and realize that in creating the electricity, you've already thrown away a huge amount of energy. From that point of view, going from petroleum to a car is actually interestingly efficient. So fuel consumption, it kind of goes along with CO2 emissions. This slide here is just for fun. We're using 86 million barrels a day. That works out to 3.6 billion gallons in the world. That's about 0.6 gallons per person per day. Remember I said in the US we use 2.5 gallons. So we're kind of using a lot more than our share. Why do we use fossil fuels? Well, as you know from just looking at this simple balance equation here, we get 48 megajoules per kilogram of fuel from, say, isooctane. What does that mean? Well, if you compare the kinetic energy of a 1,000 kilogram automobile traveling at 60 miles per hour, it works out to about the amount of energy in 1/3 of an ounce or a teaspoon of isooctane or gasoline. So a huge amount of energy comes from breaking these bonds and creating CO2 in water. So here, this is also interesting. If we compare the CO2 that's produced, 1 billion vehicles, let's just pick that number there just as a rough number. And let's say that we're burning what the US rate is, 2.5 gallons a day. You can figure out that that corresponds to about 8.5 billion tons of CO2 that's deposited into the atmosphere every year. So there's another device that uses energy, the human. We exhale, or our exhaust product, CO2 as well, right? We put out about 2 billion tons of CO2 per year. It's kind of interesting to look at those numbers because you realize that humans actually put out a lot of exhaust gas. In fact, this is a very rough estimate. The estimates range between 15 and 20% of the total CO2 comes from us breathing. You wonder, well, why? Where's all that CO2 coming from? Well, all that energy that we said that we were consuming that goes into agriculture and transportation and so on, eventually goes to feed us, and we provide CO2. So if you combine all of these things and do a rough estimate, you can see that every year we're adding about 1.7 parts per million of CO2 to the atmosphere, which is about what people measure. So this is a problem that's not just automobiles. If you look at the energy and where it goes, this is a picture that is very illustrative. If we take the fuel as being 100%, and of course it's not, right? Because in order to get the fuel to the gas station, we already lost about 20% from the well to the gas station. But let's just say we had 100% of the energy there. What comes out of the engine is about 18.2% out of this 100. Big loss is the engine. 62.4% is thrown away in the engine, in your typical spark ignition engine. 17% goes in basically standby idle. If you then consider the losses in the driveline, another 5% there, what eventually makes it to the wheels is 12.6% of the total 100. And this is partitioned into aerodynamic drag, overcoming that, rolling resistance, and so on, braking. So if you add this, plus I guess it's useful work, your accessories, air conditioning, and so on, you find that it's about roughly 16% of the total fuel here is actually doing anything useful. Actually, that number is an overestimate. Professor Hayward has an example where he concludes that actually it's about 1% efficient. Because if you look at what the weight is of a car, it's about 4,000 pounds, typical car, and the average occupancy per person, the weight of the person, and what's required to move that person, you find that the 16% times that weight ratio works out to about 1%. So cars are really inefficient, but we love them. Okay, so along with this huge use of fuel is the production of CO2. As I mentioned, 37 billion tons of CO2, about 6 tons per person in the world per year. Of course, other emissions are also produced, nitric oxides, particulates, and there's a lot of discussion about those. Well, CO2 is implicated, as you know from, I'm sure, many of the discussions this week, implicated in climate change. And of course, it's linked directly to fuel efficiency. So you want to look at your engine efficiency. Diesel engines are 20 to 40% more efficient than spark ignition engines. So that makes the case for diesel engines. However, diesel engines have higher NOx, nitric oxides, which are also implicated in environmental issues, and particulates. So they have serious environmental and health implications. There have been significant efforts to clean up diesel engines, and in 2010, for example, the United States EPA set very tight legislation, with the result that diesel manufacturers now use a variety of methodologies, for example, selective catalytic reduction after treatment for NOx reduction. We'll talk a little about that. This uses a reducing agent, carbamide or urea. And it's not free, right? This is basically the same cost as diesel fuel. And essentially, you have to take that into account when you start looking at fuel efficiency. Also, soot is controlled with filters that have to be regenerated, essentially burn the stuff off the filter. And this imposes additional fuel penalties. When you add these penalties together, this 20 to 40% here is reduced. And that reduces some of the advantages of the diesel, but the diesel is still the most efficient engine known to man. So you can see that because of the huge quantities of fuel that we use and the impact on the environment, new technologies are urgently needed to improve the efficiency of engines. We need to optimize these engines to balance the emissions, the fuel cost, and market competitiveness. What I'm going to tell you about in these series of lectures is some of the work that is going on in the area of CFD modeling of engines. This technology is increasingly being used by the industry to reduce the time that it takes from the inception of an idea to the production of a new engine, and made possible by drastic increases in computer speed. In the last 15 years, 10,000 times faster computers were used back then. And this significantly reduces the need for expensive testing. Well, another factor is that the physical processes that occur in an engine are now better understood, and the CFD tools are becoming mature enough to help in the development of cleaner engines and more efficient engines. New engine concepts have emerged, such as homogeneous charge, premixed charge compression ignition, reactivity-controlled compression ignition, and we'll be talking about some of these. They offer dramatically improved engine efficiencies and can be themselves optimized with the use of CFD tools. Okay, so let's just talk a little bit about CFD. As Ed mentioned, in the mid-70s, we had the so-called Arab oil crisis here in the US. I remember living here in Princeton at the time. They were rationing gas. You could only buy 5 gallons at a time. And worse than that, the only place you could get it was on the New Jersey Turnpike. So you'd have to drive down there to the closest exit, fill up your tank, and then use a significant part of that to get back home again. So it was actually a significant event in the history of the United States. And the government essentially said, we need to solve this problem. Let's get the national labs to convert some of the defense codes, the weapons codes, into codes that can be used for engine design by the automotive industry. So the Los Alamos National Lab and several universities and automotive companies got together, produced a whole series of codes culminating in these Kiva codes that were widely, still to this day, widely used in the industry. Other open source codes have appeared, such as OpenFOAM, as widely used in Europe. Along the way, entrepreneurs saw the advantage of commercial codes, and in the Imperial College and other places in Europe, codes were developed and commercialized, such as StarCD, the AVL Fire Code, Ricardo's Vectus Code. Fluent was also a player. And then more recently, Converge, Forte, and a number of other commercial codes are available for engine simulation. A variety of meetings where people congregate to discuss developments in CFD engine simulation, such as the International Multidimensional Modeling User Group meeting sponsored by Cray, and various other Society of Automotive Engineers meetings. Okay, so that's kind of a background on the history of CFD codes. What is it that they're trying to do? Well, if you look back at what an IC engine does, is you want to essentially convert the energy contained in the fuel into useful work as efficiently and cost-effectively as possible. To do this, you have to basically identify the thermodynamics that govern reciprocating engines, describe the hardware and the operating cycles, and then essentially look at the approaches used to develop combustion and air handling systems. So the picture on the right here basically summarizes an internal combustion engine. You have oxygen, you have fuel. They are mixed in some way in the engine. Combustion is initiated and leads to products, and one extracts work. And the important thing to realize here is that the energy release is internal to the system. The working fluid undergoes a change of state from fuel, oxygen to products. And of course, work is extracted during a cycle. So this is a little different than the textbook heat engine, which is an external combustion device. Maybe it's easier to analyze thermodynamically. Basically, you have a heat source, a heat sink, and as a result of the heat transfer, work extraction. The important thing to realize, though, is that basically here the working fluid doesn't undergo a change of state. This is a reversible process. And so some of the restrictions associated with the Carnot cycle do not carry over to the IC engine, and vice versa. So just something to remember, that your textbook Carnot cycle is not necessarily the whole story when it comes to internal combustion engines. So I'm glad to see many hands were up there, so we don't have to spend a lot of time on this slide. Basically, reciprocating internal combustion engine. We have our piston. Here's the combustion space. We're showing the piston here at top dead center. As the crank rotates, the piston moves, slides up and down. Here's bottom dead center. The air introduction is handled through the opening and closing of intake valves, and exhaust, the same thing. Some of the definitions here, we've got top dead center, bottom dead center. Compression ratio is basically the ratio of these two volumes, the top dead center and the bottom dead center volume. The stroke is the distance that the piston travels in a cycle. The bore is the diameter of the piston. The displacement would be the change in volume times the number of cylinders. And then we have some definitions here, P being the brake power, typically measured in kilowatts. The torque, or brake torque, would be in Newton meters, which is the work that we spoke about in the previous slide. Then there's the brake mean effective pressure, which is essentially a way of gauging the force that's transmitted by the high pressure gases to the piston. The mass flow rate of fuel, grams per hour, and the brake specific fuel consumption. So these are all things that are metrics that we need to take into account when we're discussing engines. The power is basically the rate of work, so work times the engine speed N here, or torque times speed gives you the power, and here's an equation. If the torque is in Newton meters, speed in RPM. The brake mean effective pressure is the power divided by displacement and the speed. And here again, depending on whether you have a 4-stroke engine or a 2-stroke engine, there's a factor of 2 difference there because we have 4 cycles or 2. Brake-specific fuel consumption is just a normalization widely used in the industry, which is the fuel flow rate divided by the power. So you'll see BSFC in grams per kilowatt hour. So I spoke about brake. This is what you would measure on a dynamometer, for example, the power produced by the engine. You have brake power. As we'll see, the brake is made up of several components. The gross indicated power, or brake quantity, refers to looking at the pressure and its effect on the piston. So that would be essentially the work associated with the thermodynamic side of the cycle. Then in order to get the air in and out of the engine, there's a pumping component that we need to worry about. And then finally, friction. You'll see in many cases the gross and the pumping are connected together, and one sees net indicated for the sum of gross and pumping. Okay, so engine power then, the indicated power is proportional to the amount of air you can get in the engine. So this m dot air is an important parameter here. Also the fuel conversion efficiency, or the efficiency of the entire process. The lower heating value of the fuel, and of course engine speed here. That's converting from work to power. The fuel-air ratio, and then whether it's a 2- or 4-stroke engine. So we're typically interested in several points on the load speed map of an engine. This curve here is typically called the lug curve. Essentially, it tells you the maximum load you can have at a given speed for an engine. There's a peak torque point and a rated speed point that's of interest. Looking at these numbers here, these are just typical numbers that you'd see in the literature for fuel consumption, brake-specific fuel consumption for SI and diesel engines. And you see they range all the way from 450 for SI engine down to 200 for a diesel engine. So one can kind of estimate what this efficiency, the fuel conversion efficiency is. And you see it's in the range of 40 to 50% if we're at this very low, relatively low BSFC of a diesel engine. It's interesting to compare that number with the number of, say, a 500 megawatt combined cycle gas turbine natural gas power plant. These power plants have just recently broken the 60% efficiency mark. They're combined cycle, so there's regeneration. They feature things like thermal barrier coatings on the turbine blades, and very, very sophisticated, millions of dollars of investment go into producing one of these power plants. Internal combustion engines can reach up to 50 and even higher for very large large engines. So they're not that different. Again, this is out of your undergrad thermo or IC engines class. Just shouldn't take a lot of time on this. Basically, if we start with the piston at top dead center, we suck the air in to the combustion chamber. Piston goes to bottom dead center. Then we start the compression process, close the valves, compress the gas. That's our squeeze here. Then we have bang, which is the combustion, and then the expansion process. And we open the exhaust. We open the exhaust here, and then we blow the gases out of the chamber. So that's just summarized over here. You'll notice there's two parts to this diagram. This part here, which essentially is the compression and the expansion strokes, and then this part down here, which looks very skinny on this plot, is the pumping loop, the part where you pump the air in and pump the air out of the engine. The engine is, in some ways, just a pump. The combustion process is typically initiated near the end of the compression stroke, maybe through a spark or through auto ignition in the case of a diesel engine. The ideal combustion process is a constant volume process that occurs instantaneously at top dead center. In a spark ignition engine, we initiate the combustion process with a spark, obviously. The air-fuel mixture is pre-mixed from entering through the intake port past the intake valves, and then we spark it, and combustion is initiated. For the compression ignition engine, we typically compress just air. At a certain moment, we inject fuel, and then we rely on the ignitability of the fuel, spontaneous ignition, to take place at the right time in the cycle. Sometimes you'll see that diesel is portrayed as a slower combustion process. Instead of constant volume, it's represented as constant pressure. And that's because the combustion process can actually be controlled by the fuel injection process. So depending on how long you take to inject the fuel, you can change the shape of the heat release part of the curve. Okay, so that's kind of all I want to say about the fundamentals of engines. Let's look at some of the models. So starting back with zero-dimensional models, by the way, you'll see in a little box on many of these slides a little name and a date here. This refers to references that you can find in, I guess, chapter 10 of the notes that I gave you. So if you want to go back and take a look at some of those references, they're here. So Hayward is a well-known textbook which describes many of the things that I'll be discussing here. In the case of a simple zero-dimensional model, this would be also called a single-zone model, where we consider the combustion chamber. We have pressure, which is considered to be uniform in space, which actually is not a bad assumption until we get discussing knock in engines, because typically engine flows are subsonic, and the pressure is therefore quite uniform. The volume is changing as a function of crank angle or theta. And so one can actually measure the pressure with a transducer placed anywhere in the chamber. And knowing where the piston is located, one can calculate the volume and see plots like this, where you'd have measured and predicted cylinder pressure versus crank angle. To understand this a little better, one can look at the first law of thermodynamics, where we have essentially the change of internal energy in this volume, the PDV work, that's the work associated with moving the piston. When the valves are open, we have mass transfer between externals and the chamber. So that's m dot would be the mass flow rate into the engine, for instance, and the enthalpy carried by those gases. And that must equal the terms associated with heat transfer or combustion. So the combustion releases energy, the heat losses to the walls and so on corresponds to Q loss. Difference between these, of course, is difficult to get in experiment, so we call that net. If we throw out this term, because now we're looking at just the closed part of the cycle, we can use the ideal gas equation to get rid of T here and relate it to the pressure and the volume, and basically we get this result, which tells you essentially the difference between combustion and heat losses, or the energy release, if you like, effective energy release in the engine as a function of the measured pressure and the volume, the instantaneous volume. So if I can use that equation and apply it to this experimental data, let's say I can get a curve that looks like this, which is the apparent heat release rate, Q net here, as a function of crank angle. You'll notice that for diesel combustion, which I'm showing you here, it's kind of interesting. It has two bumps. First bump is associated with what's called the ignition delay, where essentially you start injecting the fuel. At a certain moment, all the fuel that has been injected spontaneously ignites, giving you this rapid rise in heat release. And once you've burnt away that fuel and the injection continues, you then have a more controlled burn, the so-called diffusion burn. So we have what's called a premixed burn and a diffusion burn. We can extract a little bit more information from a plot like this by using some kind of empirical relationship for the heat loss term involving the heat transfer coefficient, the surface area of the combustor, some estimate of the wall temperatures, and the temperature, again, coming from the ideal gas equation, for example. And actually back out Q combustion. Generally, what you find, though, is that this effective heat rate here is very close to the combustion rate. Okay, so three-dimensional models. Now we look at the partial differential equations that describe the combustion process in the engine. For the 0D model, we were just looking at time variation. Now we need spatial derivatives as well. You've seen these equations before. This is mass conservation. Here's the rate of change of density at maybe in one of the computational cells in your domain. This would be the flux of mass in and out of that cell. And this would be a source term that may be due to mass being deposited in a cell from vaporizing droplets, let's say. For each of the species, now we have a partial density for each species, M here referring to that particular species. We have a similar equation, but now we have diffusional terms as well. We need a diffusion coefficient. We have combustion source terms and also possibly spray source terms. Here's our momentum equation. We have drag forces associated with the spray. We're going to talk more about those tomorrow. And then looking at the energy equation, again, we have convective terms. I is the internal energy in our computational cells. Here's our heat flux and species flux terms, combustion, heat generation. A heat transfer term associated with the spray. As the droplets vaporize, they essentially take energy from the gas. Here's a PDV work like we saw before, and then a dissipation term. So those are the equations that are solved in codes like Kiva. This reference here to the Kiva manuals gives all of the equations in great detail, so I'm not planning to spend much time on them at all. One of the things that's really important in engines, though, is turbulence. And as we'll see, it explains why engines work. So this is a one-slide review of turbulence. If you take a probe in a turbulent flow and you measure the velocity as a function of time, you'll get this wiggly line here. All right. Now, what does that mean? Well, essentially, we have velocity fluctuations of about a mean. The mean is shown with this capital U here, would be the solid line. And the U prime would be the fluctuating velocities. Those fluctuations are characterized also by a time scale associated with the turnover of eddies in the turbulent flow. And models have been developed to try to describe this turbulent flow. And one of the most successful is the Reynolds average Navier-Stokes models, or the renormalization group K epsilon models. So K basically is to take that fluctuating velocity term and convert it into a kinetic energy. There should be a prime there. Associated with the kinetic energy associated with these fluctuations are length scales of these eddies. I mentioned the time scale. If we multiply by the mean flow, we can derive a length scale using Taylor's hypothesis. And then another quantity that's of interest is the epsilon, the so-called dissipation rate of turbulence, which you can get knowing the turbulent time scale from this equation. Or vice versa, if we have an equation for the dissipation rate, we can get the time scale. So the K epsilon model essentially is a set of partial differential equations that solve for these quantities K and epsilon. You'll notice here's the rate of change of turbulence kinetic energy. There's a production term, and the production term is shown over here. You have so-called Reynolds stress terms times a characteristic time, which is determined from the mean flow strain rates. So gradients in the mean flow have units of time, inverse time. And so that's a time scale. And the product of the velocity, this tensor here, is a stress tensor, so-called Reynolds stresses. Here's the equation for the Reynolds stresses. So that gives you the production term. Then we have this dissipation term. So turbulence, once it's created, is dissipated by viscous action. And the rate at which it's dissipated is this epsilon. And then the diffusion terms. So taking this equation and writing a very similar type of balance for the dissipation rate, you see here there's this production term again multiplied by this inverse time scale with a constant. Then we have dissipation of dissipation term, again another constant, diffusion terms, and a term that involves compressibility, which is important in engines. This term R here comes from the renormalization group theory, where essentially you recognize the fact that the turbulence can be out of equilibrium. In other words, there can be different timescales for the turbulence and the mean flow variation. And this parameter epsilon here, epsilon, measures the ratio of the turbulent time to the mean flow strain time scales. And this correction term from Jakob and Ozak, who developed this RNG model, allows you to sharpen your estimate of the dissipation rate equation. So the important thing about this slide is that two parameters are solved along with the Navier-Stokes equations, namely K and epsilon, and from those we can get the turbulence kinetic energy and a characteristic timescale for turbulence. Okay, so this is just a real brief summary of the Kiva code, for example, where basically the flowchart for solving those equations is discussed. It's divided into initialization, phase A, phase B, and phase C. Essentially, you, at each time step, look at where the piston is located, do some preliminary calculations, then you do your spray and chemistry and associated modeling in phase A. In phase B, you do the fluid phase calculations, as described here. And then phase C, you remap the mesh. So one of the things that's interesting there is how do you handle a moving piston. So this might be a picture of your mesh at a certain time. This refers to the position of the piston in that mesh. During a time increment, your piston may move to a new location. Once it's moved far enough, you decide, well, I'm going to combine these two cells into one cell. So essentially, you remove this boundary here. So now you have just one cell. And now the cell below is no longer active in the calculation because that represents part of the piston. So this snapping approach allows you to deal with moving valves and moving pistons, and is very effective for these type of geometry varying calculations. Okay, so let's look at one-dimensional codes just very briefly. They are widely used in the industry. As I mentioned, AVL and Ricardo also have multidimensional codes. Probably the widest used code in the industry is from Gamma Technologies, so-called GT Power. And what these codes do is they can predict wave action in the manifolds by writing down the conservation equations in one dimension. So for example, in this picture you see here, if the piston moves a little bit and the valves are open, I need to communicate that information with the outside world and draw in, suck, in the words we used earlier, fresh air into the chamber. However, you notice that it takes quite a while for that information to get from the piston all the way back to the environment to tell the environment that the piston has moved. And in fact, if we had a 1 meter long resonant duct here, you can see it would take, with the speed of sound, 330 meters per second, about 3 milliseconds before the outside world knew that the piston had moved. If you look at an engine operating at 1800 RPM, 1 crank angle degree is 0.1 milliseconds. So this corresponds to about 30 crank angle degrees of movement to get information back and forth through this duct. Well, all of this wave propagation is calculated for you in these one-dimensional codes. Here is the environmental or ambient plenum. This is a palette that you set up when you set up one of these codes. You go through various ducts and unions. Here's your compressor, which of course will be connected to a turbine. And then here's your, in this case, a 4-cylinder engine, your 4 manifolds. And here are the actual cylinders. And you would specify valve timings and so on. And the 1D code would do the calculation for you. So just looking at the equations, basically we're dealing with a one-dimensional model here. So we subdivide our domain into steps of dx. Of course, the cross-sectional area at each position down the duct has to be specified so that the volume of each of these cells is the area times dx. And then one applies the Reynolds transport equation, which essentially allows you to derive the conservation equations for mass, momentum, and energy. And I'll just write them down here. This would be your mass conservation equation for density changes for the local cross-sectional area A, and the one-dimensional velocity v. These variables are functions of x and t, space and time. Here's your momentum conservation equation, pressure gradient, and then this term here represents the effect of friction, which of course in a one-dimensional flow you can't really calculate because friction is a multidimensional effect at the walls. So you have to specify a friction factor, and that's typically done through using some correlation for the wall friction. Similarly, for energy conservation, we have a dissipation term that involves that friction, and then we have a heat loss term that has to maybe use a wall heat transfer correlation to provide the local heat transfer. And here's our PDV work again. So these are the conservation equations that are typically solved in one-dimensional models. And you can read up on those in various textbooks. Of course, the gas exchange process is more than just a one-dimensional problem. Here we have to deal with the flow as it enters past the valves. There's significant losses associated with the flow speeding up through that valve area. It's very dependent on the history of the valve lift, shown here, for example, the exhaust valve lift as a function of time. The intake valve lift, there's a period where both valves are open. So you can, if you're not careful, you can have intake flow just passing straight through the engine and out the exhaust. Typically, though, because of those delays that I mentioned associated with the flow in the manifolds, that effect is not, it can be calibrated out. The other thing that the intake flows generate are very complex flow patterns inside the combustion chamber. They lead to swirling flows, tumbling flows, and these flows are encouraged in many engine designs to increase the turbulence in the engine. And again, a 1D flow simulation cannot give you any of this information. So essentially what you need to do in a one-dimensional flow calculation is to use experimental data to essentially correlate flow effects with, say, swirl in the chamber or with flow losses across the valves. So this is kind of just says what I just said. You might use a multidimensional calculation to actually calculate the pressure drop associated with the valving, and then feed that into your 1D code. Flow losses that occur at bends, such as the flow not being able to negotiate this tight bend here, can also be included as lookup parameters in a 1D flow code. And in fact, in those 1D codes, you'll see basically most of the code is associated with these types of models that are read in. For example, in the Ricardo wave code for duct bend losses, now we're dealing with a duct that has a change in cross-sectional area and a change in direction of the flow, so we might have some sort of flow separation taking place. Correlations have been developed that are used in the code that essentially take into account the change in diameter and the radius of curvature of the duct cross-section and so on. So a lot of work has been done over the years to make these codes smart. Of course, we want to run those codes because they run a lot faster than multidimensional codes. Well, why are we interested in this? Well, one of the main parameters that affects engine performance is how much air you can get into the combustion chamber. And this is essentially referred to as volumetric efficiency in the literature. So m dot air, or m air, here's the mass of air that you can trap in the cylinder when the intake valves close. The air density is important, and of course the volume of the combustion chamber. Determine the product of these two is the mass. So this volumetric efficiency, as I mentioned, depends on losses that occur as this flow speeds up past these valves, the nature of the flow field itself, and really you can only get this type of information from either experiment or from detailed 3D calculations like I'm showing you here. Not to be outdone, in the 0D codes, what they do instead is the user has to provide tables of flow coefficient or flow loss as a function of the valve lift to diameter ratio. So this is just an example of an input to a 0D code that essentially is the flow coefficient versus the valve lift normalized by the valve diameter. And so here's a very simple layout for a Ricardo wave 1D code. We have our intake environment, atmosphere here, a duct. Here we have just a simple union. And then this region here is handled by the valve, and the flow coefficients are then read in, as you see here. On this side would be the corresponding exhaust. We would have a similar looking lookup table for the exhaust valve flow coefficients. Okay, so what do you do with all of this? Well, you can now optimize an engine, because once you've laid out your engine, here's an example with GT Power. Here's one of the cylinders of a multi-cylinder engine. Here's your cylinder number 8. It's 2 intake valves and 2 exhaust valves. You can adjust the lengths and the geometry of these manifolds and see what effect it has on the amount of air you're able to trap in the combustion chamber or the volumetric efficiency. So these plots here show what happens, a little calculation that was done looking at what happens when you change the exhaust runner length. That's this piece over here. There's 4 different cases going from 300 to 600 millimeters. And as you can see, this plot, this axis is volumetric efficiency. There's quite a significant change in volumetric efficiency, especially at low speed here, because obviously the length of that duct has to do with information propagating from the environment back to the cylinder. The plot on the right shows the same thing, but now we're changing the length of the intake runner here. And again, you can see over a certain range of speeds, this has a significant impact on volumetric efficiency. Notice that the volumetric efficiency drops off at low speeds and also at high speeds. We'll talk more about that in a minute. Another way of optimizing volumetric efficiency is to actually change the valve event itself. So here we see the valve lift curve as a function of crank angle, the exhaust valve open and close. And we can, using what are called cam phasers, move the whole profile to the left or the right, depending on, say, engine speed. And so, for example, you see here a case where the entire profile is delayed. We minimize the amount of valve overlap by doing that. And this has a significant effect also on volumetric efficiency. And this final plot here shows an example. If we take the baseline engine, that's the blue here. This is volumetric efficiency, or the amount of air I can get into the combustion chamber versus speed. The baseline is the blue here. I can achieve this red curve by optimizing when those valves open and close. And there's a significant improvement. We're going from like 93 to 96% here. 3% improvement in amount of mass means 3% more fuel available for combustion in the case of a spark ignition engine. This idea you'll see represented in many different forms. This was an early concept of Mercedes-Benz, a 3-stage resonance intake system. So it's a little hard to see here in this diagram, but anyway, the fresh air comes in through this duct here. And you'll notice there are 2 butterfly valves. These valves can be opened or closed. And when they're opened or closed, what happens is effectively you change the length of the runners going into the combustion chamber. So for the shortest runner length, the volumetric efficiency follows curve 1 here. But if we then open and get an intermediate runner length, we can get, well, the longest runner length is curve 3 here, and the intermediate would be curve 2. So by appropriately changing the length of the runners and essentially this resonance effect, we can maintain a high volumetric efficiency over the whole engine speed range. So those of you who may have been involved in Formula SAE at your universities probably know all about this. How many were involved in that? Okay, quite a few. So I'm lecturing to the choir here. Okay, so this is a final plot that I wanted to show for this segment, which is out of Hayward's book, which I think is really instructive, where he discusses basically why the volumetric efficiency curve looks the way it does. So here's volumetric efficiency, and here's piston speed or engine speed. So if we just start from this baseline point here, where line A, we're going to eventually go to line G. So the factors that contribute to this shape that we discussed before are going to be discussed with this figure. So from A to B, what this accounts for is charge heating. So as this air is coming down the intake manifold, it's being heated by the cooling water jackets and so on in the head. The density of the gas is reduced, and so you can get less air into the chamber, because remember, density times volume is the mass of air you get into the chamber. And this is particularly important at low speeds, because you've got a lot of time for that heat transfer. So at higher speeds, that effect is less important. On the other hand, going to curve C here, which is this one here, as you increase speed, friction becomes important. So you have stresses, frictional stresses, flow separation, all kinds of stuff going on in the manifolds that lead to relatively large losses as the speed increases. The next is going down to curve D here, and that's what's called choking. So if at any point in the system, and formula guys know this one as well, if at any point in the system the flow reaches sonic velocity, the flow passage becomes choked. You cannot get more mass flow through the system. And so basically that leads to this big reduction in volumetric efficiency as a function of speed. Now the next effect that brings you up to curve E is the so-called ram effect, where if the gases are already moving into the combustion chamber and the piston starts moving up, you would want those gases to go out of the intake valves if they're still open. But because of the fact that the gases are already moving into the chamber, you can force more air into the chamber than you would normally be able to do, and that's the so-called ram effect. And then finally, to get us up to line G here, is the so-called tuning effect, and that has to do with those resonances associated with the length of the passages that I discussed before. So if you combine all these things together, it explains why there's kind of an optimum in the volumetric efficiency for a particular speed, and why you want to spend some time designing the manifold system for an engine in order to cram as much air as possible into the combustion chamber. Okay, so just to summarize this first hour, transportation uses about 1/3 of the total energy use in the United States. Internal combustion engines can be among the most efficient power plants known to man, but research is needed to improve them further, and we're going to be talking about that in this series of lectures. Just looking back at the energy use here, it's interesting to see the US uses about 20% of the world's oil, China 10%, India, Eurasia another 20%. These numbers are going to change, obviously, as China, for example, uses more fuel. That's going to lead to significant problems in the future, in my opinion, in the opinion of a lot of people. So industry really faces significant challenges, and one of them also involves emissions regulations. This plot here, we'll be talking more about emissions later, but it summarizes where diesel engines have come in the last 20 or 30 years. Prior to 1988, there were no restrictions on NOx. Engines were running with 10 grams of NOx per horsepower hour. It's a huge amount of NOx. Right now, in 2010, engines have to run with 0.2 grams of NOx per horsepower hour. So huge reduction in NOx. And here's particulate. Again, in no standards prior to these dates. Now we are down at 0.01 gram per horsepower hour particulates. So this is what engines of today look like. Major accomplishments in terms of cleaning up engines. So, any questions? My plan is to kind of give you half of the next lecture now, and then we'll break at 10:15. Yeah?
From a modeling point of view, what temperature range are we typically looking at in engine modeling? Do we go all the way from room temperature to like 3,000 Kelvin?
Right. So in a spark ignition engine, naturally aspirated stoichiometric engine, the temperatures can be 2,700 Kelvin or higher, 2,800.
At the lower end?
Room temperature, yeah.
And pressures?
So again, depends on the engine. You know, heavy-duty diesel engines can go up to 200 megapascal type of pressures. Typically, for a spark ignition engine, you're at 120, 130 megapascal.
We need bars or
PSI. Bars, thank you. Thank you. Yes?
What are the main differences between HCCI and RCCI?
We're going to talk about that a little bit later. So can I hold off on that? I just want to, I can just summarize in one step here. HCCI is homogeneous charge compression ignition. So the whole chamber is filled homogeneously with a fuel-air mixture. PCCI has gradients of fuel-air mixture in the combustion chamber. RCCI is like HCCI, but it has gradients in fuel reactivity in the chamber. And we do that with two fuels, one reactive fuel and one less reactive fuel. And we'll discuss that later. Yeah?
Talk about maximum size for piston engines, say for stationary power. What's really the boundary there?
We were just talking with Mitsubishi Heavy Industry, and they asked us if we could model an 870 millimeter bore ship engine. So the piston is, I can't even stretch that far from it. So this engine's the size of this room. It's just complexity, I think, is the upper limit. And then, I don't know if you guys played with toys when you were small, but if you had those little model airplane engines, they're very tiny. Huge range in engine size, which is something we're going to talk about here too.
As we're increasing injection pressures and in-cylinder pressures, what differences and challenges do you see in the computational world for
Yeah, that's a good question. So, you know, just from a fluid mechanics point of view, cell size and velocity imply a time scale because a fluid has to move across a computational cell in a certain time. So if one has higher velocities, smaller cells means smaller time steps, which means, you know, longer computer time. But then there's the whole issue of the modeling. Are our models good enough to represent what happens when you go to really high injection pressures? We'll talk more tomorrow about spray modeling. There was another question.
I have one.
Okay.
So one issue that has become pretty popular recently is formation of these deposits in diesel injectors.
Right.
How big of an issue is that really?
Huge.
Efficiency losses.
Well, I think the issue there is you cannot really tolerate them. So there's nozzle design is really important. Fuel formulation is very important. And then, you know, ways of monitoring the performance of an engine over, they have to be basically warranted for 450,000 miles for heavy-duty engines. And, of course, during that period, the nozzle flow is affected by deposits. The engine still has to perform according to that picture I showed you, meet those emissions regulations. So it's a big issue.
And there's not much understanding right now at this point about.
Well, there are whole SAE sessions with papers on that. So, I mean, there's understanding, but it's not a solved problem. Yeah.
By the time you find these open source geocodes.
Where? I think I have a reference there. But anyway, if you just Google Kiva code, you'll see it's the Energy Science and Technology Software Center. It's a DOE depository. And I forget what the cost is, but it's not a lot, you know, maybe $1,000 or something like that. But you get this, you get the code. Your advisor can buy it for you.
Could you elaborate on the boundary condition treatment when you have a moving mesh, and also for wall function on the turbulence model?
Sure. Probably going to talk a little bit about the wall function stuff tomorrow. In terms of the moving mesh, that SNAP algorithm that I mentioned is probably one of the most popular. One can also use a so-called accordion mesh approach, where the whole mesh just expands and contracts. The problem with that is because the stroke is so large, if you start with a certain number of cells, they will be very, very tiny cells at top dead center. So generally you want to throw out cells using like the SNAP approach. It's an interpolation. You know, you have those two cells, one of them has changed its volume. And at a certain moment you want to combine them, so you've got to do interpolation of mass, momentum, and energy. It has to be done accurately, otherwise you can see problems. But it's just a detail, really. Yeah.
You mentioned earlier that internal combustion engine is not limited by Carnot cycle. Can you elaborate on that?
Right. Well, a lot of the things that we're going to be talking about, like, for example, the fact that you can have a lot of unburnt fuel in the exhaust, that's not accounted for in the Carnot cycle. What do you do with that unburnt fuel in reality? It obviously affects the efficiency of the engine. That's not in your theory in the Carnot cycle.
Sort of on that same note, you brought up the internal versus external combustion. And when you see some of these other interesting cycles, like the Stirling cycle, one of their difficulties is the high temperature reservoir. The whole engine has to withstand it. But it brings up a question I'm really just not familiar with is how hot can you get flame temperature inside an internal combustion engine before it still damage the construction material? Is there an upper bound that people are working with right now?
Yeah, that's a really good question. You know, gas turbine engines, you guys all had a course on that, and you probably heard that, you know, the maximum temperatures are limited by the blade temperature that the blades can withstand, typically less than 2000 K. The reason internal combustion engines work is, one of the reasons, is because they can withstand much higher temperatures because it's intermittent. So you have time to cool things down before the next cycle. But, you know, the yield strength of materials drops drastically with temperature, so you have to worry about that. You know, so I think a practical upper limit would be, like I mentioned before, 2700 K, somewhere around there. But I'm going to show you later, you really don't want to operate there because along with 2700 K comes 10 grams of NOx per horsepower hour. High temperatures giving you very high NOx. And NOx abatement is a big issue. So low temperature combustion, less than 2000 K, is very much more attractive. The other thing is that when you have 2800 K, delta T across the surfaces is very large, so you have high heat losses, and that, remember the 60% of the energy we throw away?
Like
That's
parasitic heat transfer.
exactly, yeah.
Energy body.
Yeah. So if you can lower the delta T, you can lower the heat loss, make the engine more efficient. I should probably move on, and we'll take, well, okay, one more.
Will you increase engine efficiency by changing the ignition system?
Right, so it's an issue of the,
How much?
okay, so that's an issue of, two things. One is lean burn operation typically requires very strong sparks in order to get the combustion to start. So that's one area that people look at is lean burn. We'll go, if we have time, we'll go into discussion of that a little bit. But the other thing is that the spark event essentially controls when the combustion takes place. And it's possible to have the combustion take place at totally the wrong time if your spark energy is not enough. So spark energy is very important. And people are looking at multi-strike sparks as well to really make sure that ignition happens. Okay, let me move on, and we can try to find some time for more discussion. So I can probably zip through this part quite quickly. So this is hour 2, and we're going to be looking at turbochargers, engine performance metrics. And we're going to do like half of this now if I can, and then continue it after the break. Okay, turbocharging. So remember I said you want to get a lot of air into the combustion chamber. Well, turbocharger is one way to do that. And if you look at the kind of trend in the industry, you'll see for both diesel and gasoline engines, turbocharging is now becoming pretty much a necessity. Here is your naturally aspirated diesel, indirect injection diesel. Here's a turbo diesel. Here's a naturally aspirated gasoline engine. I'm measuring torque here against specific power in kilowatts per liter. You can see this trend of increasing torque, increasing power density, and it's really associated with the turbocharger. How much air can you push into the combustion chamber? Because the more air you have, the more fuel you can put into the engine, and therefore the higher the power output. So the purpose of turbocharging is to increase the air density, the amount of air. Several ways you can do it. Here's a nice picture that summarizes that. So here we have in red the exhaust gases. They come out and they can actually bypass, but some of the air goes through a turbine and then is vented to the atmosphere, obviously through exhaust after treatment systems and so on. And then the turbine itself drives the compressor. So here's your fresh air. We come through an air filter. We can bypass this here with a valve and use just a mechanical turbocharger or a supercharger that's driven, it's like a Roots blower that's driven by the engine itself. Or we can use the compressor down here, or both. The idea is to get as high a pressure in the intake manifolds here as we can. So here fresh air is going to be passing through the compressor. We can also have a bypass here through a cooler and then into the engine. Okay. Here's just another picture that shows the compressor turbine arrangement and the so-called waste gate, which essentially says if I don't need all of that exhaust to drive my turbine, I can send some of it out of the exhaust without passing it through the turbine. So here, let's see, here's the exhaust gases passing through the rotating impeller of the turbine, and here are the fresh gases passing through the impeller of the compressor, and that's just a little picture of the inside of one of these devices. Here's our charge air cooler, because once you compress that gas, of course, it heats up, and you've got to get rid of that heat. So this becomes a major issue for the entire system, right? You've got your engine here, but now you've got another engine over here to deal with, plus heat rejection. And in fact, some systems are even more complex, where you'll have a low-pressure turbine followed by a high-pressure turbine. In other words, the exhaust gas drives first high-pressure drop turbine and then a low-pressure turbine. And of course, in a multi-cylinder engine, you may have several of these devices hooked up, like in this case for a V8 engine. You're going to have 4 of these things. Here's a picture of one of those. These things can be modeled in GT Power and those other codes that I mentioned as well. And so one can look at the performance of the entire system with those system simulation codes. And that's routinely done by all of the engine manufacturers. This chart here just sort of summarizes something I wanted to mention. So here we have our compressor, then we have a charge air cooler, and then the piston cylinder arrangement here. If we plot cylinder pressure versus crank angle or volume, in this case, going from the volume at intake valve closure to top dead center, and if we assume isentropic compression, we follow a line like this. Now, during this process, the temperature in the chamber is also increasing. And if we had a pre-mixed mixture of fuel and air, like in an HCCI engine, for instance, a certain temperature would be reached where combustion would take place. And if the combustion was very fast, like in HCCI combustion, we would have a constant volume combustion process. Piston's still on the way up, so we would have some compression, raising the pressure and temperature to possibly values that exceed those of the design of the engine. And then we would follow an isentropic compression, expansion path. So all of this shaded area here is work that is thrown away, potential work that's thrown away, because we had combustion taking place too early. So one of the things that's key here is to get the combustion to take place at the right time, which is, as you can see from these diagrams, ideally at top dead center. So if we add a compressor, like we see here, essentially at intake valve closure, everything moves up, right? Because this is the amount of boost that has been provided by this compressor. And you can see that we might even have a worse situation, reaching even higher pressures in the combustion chamber that could lead to damage in the engine. With the charge air cooler, though, we can keep the temperature the same as it was before. So we still follow this temperature plot here. If, however, we delay the time that the intake valve closes, so we can start from this boosted pressure here and start from a lower temperature, essentially the temperature that we would have had coming out of the charge air cooler here. And now, when we compress, we can reach this ideal state where ignition takes place at top dead center. So in that case, what we've done is essentially we've regained this shaded area that was lost. So the combination of variable valve timing or intake valve closure control together with boost and charge air cooling is very effective in engine combustion. And those are tools that designers use. Okay, so getting back to the compressor, typically, this is a picture of it here. Typically, there are centrifugal compressors. They run at pressure ratios up to about 3.5. They run at very high speeds, 100,000 RPM, for example. Let's see. If you want to understand compressors, it turns out that a really good assumption is to look at them as isentropic compressor devices or expansion devices in the case of a turbine. You remember this from your thermal classes probably. So if we just take a quick review of isentropic compressible flow theory, there's only one equation that's really important, and that's this one here, that relates the stagnation temperature, the temperature when the gas is not moving, to the local temperature and the Mach number. How do you get this? Well, this comes from that energy equation when you assume no heat transfer and no frictional losses. In other words, du and the PDV term only. This is the equation that you derive. If you assume isentropic flow, you can actually get the pressure ratio also from that same equation. So we use this in our isentropic flow courses, for example, to study what happens when you expose high pressure reservoir through a converging nozzle to a low pressure ambient. If the pressure in the ambient and the reservoir are the same, we have no flow and the pressure is uniform throughout the duct. As we lower the ambient pressure, you can see we follow a path such as this. If we lower the ambient pressure enough, in fact below 0.528 here, which depends on your value of gamma, which I've assumed to be 1.4 for diatomics, you reach the point where the flow at the exit becomes sonic. The Mach number becomes equal to 1. And the flow becomes choked. And we spoke about that earlier. So now, no matter what you do with the ambient back pressure, you cannot get any more flow through that nozzle. So an example where that becomes critical is flow past a throttle plate in an SI engine. So here's a throttle plate in a duct. Depending on how you open this throttle plate, the cross-sectional area here becomes different. And so for a fixed position of the throttle plate, you get a plot that allows you, as I've shown here, the mass flow rate through the duct as a function of the pressure drop, or the manifold pressure. That would be the downstream pressure here. This is in centimeters of mercury, so 760 is atmospheric here, 40 is 0.528. So as you decrease the back pressure, or throttle the engine, you get more and more mass flow up to a certain point where the flow becomes choked, becomes sonic. Now if I want to, I can open this throttle a little bit more and move to a new line here, in which case the choking occurs at a larger area and I can get more mass flow through the system. So these curves of mass flow versus pressure are kind of fundamental to this flow situation that we've described here. In the case of turbo and compressor, instead of having a converging flow here generating this change in pressure, we're using a wheel that's essentially speeding up the flow in the compressor device. Okay, so this leads to an equation that's called Fligner's formula. Essentially, it says how much mass flow can I get through a duct. The mass flow is the density times the area times the velocity. And if you work through the math here, you can see that for the choked flow situation, where the Mach number or the velocity is equal to the speed of sound, the Mach number is 1, it depends on the reservoir pressure, the reservoir temperature, and the local area. So that's Fligner's formula. And this is used in the compressor and turbine community to essentially provide a measure of the effective flow area in a duct by normalizing this mass flow rate by a temperature, the square root of temperature, and pressure ratio. And so you'll see plots like this of normalized mass flow rate and normalized pressure and the choke flow point. And these different lines correspond to different passage areas. So you'll see that kind of plot when turbo machinery is characterized. So if we just look at the compressor, here we have the flow entering the compressor at, let's see where at state P0 in here. The flow slows down, speeds up through this converging passage here. So at the entrance to the rotating impeller, the pressure is P1. Then if it was isentropic, essentially we would have an isentropic process bringing us up to the exit of the compressor wheel. And then we'd have a diffuser that follows that to slow down the flow and regain some of the potential energy in the flow, and that brings us up to P3 here. So you can represent a compressor by a path like this on a TS diagram, S being entropy, and if it's isentropic, everything follows a vertical line. You can estimate the compressor work by looking at the mass flow through the compressor and the difference in enthalpy of the intake and the outlet flow. And again, assuming isentropic flow, you can relate that to the pressure ratio across the compressor. So this formula here for the compressor work is used widely in 1D codes, for example, to calculate the pressure. The compressor work. Of course, in reality, the flow is not isentropic, and there are losses. And so one has to introduce this quantity here, the compressor efficiency, eta C here, which essentially measures how much entropy is introduced that deviates from the ideal process. So looking at this diagram here, this is a compressor map that a compressor manufacturer would provide with their compressor. This is the pressure ratio. This is the mass flow rate. So this is kind of, if you rotate this plot and turn it backwards, it's the same as the ones we saw before for the throttle vane problem. You have your choked flow point on this side here. On this side, you have the so-called surge line. This represents at low mass flows and high pressures, you can have flow separation in the ducts within the compressor, and is referred to as the surge line, as you see here. So essentially, a compressor works between the surge limit and the choke limit. These islands that you see here are lines of constant compressor efficiency. Typically, you'd like to operate in this region where the compressor efficiency is the highest. These different lines correspond to different speeds of the compressor, different blade speeds, which is like opening the area when we were talking about the throttle valve situation. So again, Hayward is a great reference if you want to learn more about compressors. Yes, just an example of a practical compressor map taken from a GM 1.9 liter diesel engine. You can see the compressor speeds here going up to 190,000 RPM and down to 35,000 RPM. This would be our pressure ratio and our corrected mass flow rate on this plot. So for turbochargers, we have basically the opposite of a compressor if you look at it on a TS diagram, where now we want to take potential energy from the high pressure exhaust and transmit it through the impeller to generate high velocities in the turbine. Go through the same kind of analysis. Here's our corrected mass flow rate curve again, using Fliegner's formula. Corrected blade speed, which again essentially non-dimensionalizes the RPM of the blade with the sonic velocity, which goes as the square root of temperature. Again, there's a turbine efficiency we have to worry about. The picture you see here is for a radial flow turbine. These are typical for automotive applications, but there are other turbines, turbochargers, the axial flow type that are used typically in large engines. So the whole point of this then is again to take our exhaust gas, the energy in the exhaust gas, and convert it into motion of the impeller, which then drives the compressor. So this plot kind of summarizes this whole concept. So here's a PV diagram once again. Here's bottom dead center of the piston. Here's top dead center. Here's the compression stroke from 1 to 2. Then we could have isochoric or constant volume combustion like in an SI engine. That's the idealization. Here for diesel combustion, you might have constant pressure combustion as an idealization. Then you have expansion stroke, and at 0.5 here, the exhaust valves would open, and you have what's called the blowdown process. Now, in a typical application, you would blow down in a naturally aspirated engine to atmospheric pressure. But in reality, what we'd like to do is to take this energy that is potentially available if we were to allow the piston to move further down, to take that energy and use it to drive the turbine. So basically, the energy that's in the shaded area here can be used to drive the turbine, which then in turn drives the compressor, which allows you to increase the intake pressure. So this part down here, if you recall, was what we call the pumping loop. Going from 5 to 7, you blow down during the exhaust process. Here you push the gases out of the engine. Now the intake valves open, and here you draw in the fresh gas, and then you start the compression again. Turns out that if the intake pressure is higher than the exhaust pressure, or in other words, P7 here is less than P1, the effective pumping loop is such that you actually gain energy. So you would like to have your intake pressure higher than your exhaust pressure, because essentially then you are gaining some work during the cycle. Remember, the work is the area under these curves. So here you can see there's this area would represent the energy released from the combustion process. This area would represent the pumping work. And this can be arranged if you arrange the turbine and the compressor appropriately. It's not always possible to do it, but it's helpful to have the intake pressure higher than the exhaust. The only caveat is this can hurt scavenging, because if the intake pressure is higher than the exhaust and the two valves are open at the same time, you can have that short circuiting that I mentioned, where the intake flow can go out the exhaust. Okay, so anyway, this diagram here, if you think about it, is essentially saying that there's still significant energy, significant expansion energy available when you reach the exhaust valve open time, and you can use that to drive the turbine. The turbine work then is the mass flow rate through the device times the change in the enthalpies. Once again, you can relate that using the isentropic flow assumption to a pressure ratio across the turbine and to a turbine efficiency. So I think I'm going to take a break here for, we have, I think it's a half hour, right? But before we do that, maybe we take just a few minutes for questions, and then we'll come back after the break. Yeah?
If that short circuiting of the fuel mixture happens, that's just a failed engine failure?
Yeah, because if it's a premixed charge, like it can happen in a port fuel injected engine, that fuel just goes straight out the exhaust into your catalyst. That's one of the reasons for the lower efficiency of a spark ignition engine. Any more? Okay, let's take a half-hour break. This is,